I will be your moderator today, inshallah. This seminar today gathers us under the umbrella of curiosity, passion of knowledge, and the eagerness to learn. We are here to learn more about this human brain imitator tool we call artificial intelligence and its different applications and how it fits this journey of digital sovereignty and national security, thus going from foundations that are purely mathematical to how we use it to strategize. This journey will be guided by two figures who have been well acquainted by artificial intelligence and its different applications, whether in computational mathematics or its foundations like algebra and cognitive science. But before I welcome them on scene, I should like to tell you that we are brought here today thanks to a collaboration made by l'association Math&Maroc that I will leave Mr. Afif Mohamed Taha to tell you more about, and also being hosted by l'école Hassaniya des Travaux Publics, notably helping in the organization students, either via Bureau des étudiants or Hassaniya Club of Mathematics, who will be presented by Mr. Mehdi. So I will invite first Mr. Afif Mohamed Taha, who is a student from Centrale Supélec and the treasurer of the association.
Yeah, thank you, Selma, for the lovely presentation. Thank you all for coming. So I would like just to speak a bit about Math&Maroc and how did we get here. So Math&Maroc was created in 2016 by a group of friends who wanted to help the Olympiad candidates have a better chance at the international competitions and a better understanding of mathematics. And in 2023, there was a group of 3 friends in Paris having a cup of coffee. And then they started discussing, why don't we create a competition for the postbac or the undergraduate students in Morocco. And this was the story of how our first event, Math&Maroc competition, was created. And it's organized every year from the 24th to the 28th of July. And I think you may be interested because you can participate. So I urge you all to check out our Instagram account and apply. I hope to see you there in the College of Computing, actually. Then in 2024, many members started coming in because of the visibility we gained from Math&Maroc competition, and we started creating more and more events. So in 2022, we had 0 events. 2023, we had 1, and now we have almost 10 events and other divisions. For example, the seminar division that organized this competition here today. And we today have almost 200 members. And we're still welcoming in new volunteers. We always have a need for new volunteers. So if you are interested, please do apply once we see an announcement. So I want to take up much of your time. I would like to thank the speakers for accepting our invitation. Thank HTP for their warm welcome, and Math&Maroc for making this possible. Thank you. Good luck.
Thank you so much, Mr. Afif Mohamed Taha. Now I shall welcome Monsieur Mehdi Ben Saud, a student at l'école Hassaniya des Travaux Publics and the president of Hassaniya's Mathematics Club. Please.
Et au nom du collège de mathématiques de Hassaniya Public, je tiens à remercier, je tiens à souhaiter la bienvenue à nous 2 éminents conférenciers et les remercier chaleureusement d'avoir accepté notre invitation. Et je voudrais également exprimer notre profonde gratitude à l'association Math&Maroc pour son engagement profond à promouvoir la science et les mathématiques au Maroc. Ainsi, pour cette collaboration précieuse qui a rendu cet événement possible. Le club de mathématiques de l'HTP est un espace pour valoriser et vulgariser et bien sûr rendre rigoureux et approfondir les mathématiques. Nous espérons que cette conférence sera une source d'inspiration et d'enrichissement pour tous. et je vous remercie pour votre attention. Merci.
Merci, Monsieur Midi, et je vous souhaite bon courage avec les objectifs de votre club. I'm going to switch back to English. And we're going to welcome our first speaker, Monsieur Ahmed Ratnani, who is an assistant professor at the Mohammed VI Polytechnical University, who's also the interim director of the Cybersecurity for Africa department at the latter. He had his PhD in applied mathematics from Strasbourg University, which was prepared at the French National Institute for Research in Digital Science and Technology. His research covered many specialties, such as artificial intelligence, obviously, high-performance computing, and numerical methods for complex systems. He's the former researcher at the Max Planck Institute for Plasma Physics, and he is here today to present artificial intelligence and national security, strategic imperatives, and digital sovereignty. So please, under your applause, welcome with me, Mr. Ahmed Ratnani.
So, hello everybody. So I'm very happy to be here with you today. And I would like to thank EHTP for organizing this event, but especially Math&Maroc, l'association Math&Maroc. You've been doing an amazing job since many, many years. And I hope that this will continue, and not only that, it will get amplified soon. Because we need such initiatives to promote the role of mathematics. People, especially in Morocco, do not understand what mathematics are useful for, especially at the industry level. So my talk today is rather very special because I wanted to talk about national security. In a sense that such a topic is maybe never discussed in Morocco. And we are in a real need to talk about it and also to advance it. You are all aware about what's happening right now in different places in the world. And it's very, very important that each one of us contributes or give back to the country. And this is really what we call national security. So we will define it later, what is exactly national security, because people tend to think that national security is about defense, army, and so on. It's not only that. This is just the core. And we will see, this talk is not a technical talk. It is more for a broader audience. And I did it on purpose because really the purpose is to open minds of young students, young researchers in Morocco about the problems that are coming and how we can make good use of what we have as resources. So today's talk is really more focused on how Moroccan talent may shape the future. So I will do some corrections because I didn't share with you guys my biography. So I'm actually associate professor, and during a time I had the privilege to serve as interim for CISA, which is Cybersecurity for Africa, and then we passed the baby to the College of Computing, who are now doing some great job on cybersecurity on the IT side. I moved to the OT side, to the operational technology side rather than the IT, for many reasons, because for industry, this is what we need. And also for defense, this is what we need. So without going further, I will just mention something newly created at UM6P, which is the College of Mathematical Sciences and Intelligent Systems. So it is a very young college at UM6P. And feel free to reach us if you want to know more about our vision, about what we want to do in this field. So the outline of my talk will be, I need the, it's fine. So the outline of my talk could be the following. So many introductions about different things, especially about what is changing right now with AI and how it is impacting different fields. And then I will briefly, in fact, recall a dual history of AI seen from the civil perspective, but also from the military perspective, which is very, very interesting. And then we will focus a little bit on defense and then go back to digital twins and the talent dimension. So this is a new strategic era. So what we are observing today is the rise of not only a new technology that is transforming the world, but it is more a mutation than a transformation. And we will understand why it is not just a transformation. So everything is being reshaped by AI, from automation to cyber physical systems to how we handle large data and so on. And all strategic sectors are concerned, from energy to agriculture, to health, to industry, to education, and especially defense. So people are now competing for more computing power or algorithmic power, computational capacity, infrastructures, but more especially technological talents. So Morocco is really entering a new era with some new dimensions, where for the first time in its history, we can make use of something that we are very good at, which is mathematics. And we see that, in fact, if you look at the Association Math&Maroc, we see a nice change in mindset, in the sense that most of all students who are in grandes écoles in France, like Polytechnique Centrale, now they're aiming to do their PhD. So it is a natural continuation today. It is not a special case, which is really great, because we need these great minds to build the future. So AI and digital technologies are now really linked to everything, as I said. And we will go step by step during this talk and see how things are getting bigger and bigger, but also how they are changing the world. So what do we mean by national security? So as I said, we usually tend to think that national security is about defense. Well, it's not. It is all the sectors that are important for the country. Education is important for the country. Energy, and we are seeing it, we are living it today with what's happening in the Middle East. Agriculture, for sure, and water, and economics and industrial systems as well. Cybersecurity, for sure, health and biosystems, and so on. So military and defense are at its core, but there are many, many other fields that are relevant to national security. And we should develop them having in mind that we are targeting a sovereignty and we are targeting national security. So a country is secure only if all these systems are resilient. So let's see here some numbers about how AI is changing all these strategic sectors. So if we look at energy, we see that the investments in AI-powered smart grids, for example, are reaching $13 billion by 2030. Predictive maintenance, you'll see that it is everywhere, and it is also increasing by something like 30%. In agriculture, we are now talking about precision agriculture, and we already observe some impact of that, which is an increase of the yields by 10 to 25%. Water optimization as well, where we can reduce it even up to 40%. And industry and manufacturing, especially through digital twins, where we can see a reduction of cost of 5 to 15%, and even the control of the industrial systems, thanks to digital twins, that can be improved up to 50%. So from the defense point of view, the global military AI is spending a lot of money. So it went from $9 billion in 2023 to almost $40 billion in 2028. So it is a very high strategic sector right now. So I left education to the end because this is really the bottleneck of everything. And as you can see, with this mutation of the world, education will also change. And there are already people at Silicon Valley who are working on future concepts of universities without professors, without everything that you know. And this is why, in fact, there is a lot of money in it, injection in it right now. But what we learn from the experiments that have been done is that personalized education increases the efficiency of learning and mastery up to 60%. And today, we already, you can already use what we call AI tutors in different fields. So this is really a very, very high strategic sector. So if we look at, in general, the growth of these different sectors, we see that the most advancing one right now is education. It's almost 25%. In agriculture, industry, it's almost 20%. In energy, almost 20% as well. And in defense, it is also growing as well. So just a takeaway for you, national security is a multi-sector challenge. It includes education, energy, health, water, agriculture, and so on. AI and digital twins are really reshaping all these fields. And we believe that Moroccan talent can help Morocco to be positioned in a very interesting role across the world. So what are the global strategic trends today in AI and digital systems? So first of all, we see a rapid expansion and convergence of AI, IoT, cloud computing, edge computing, and cyber-physical systems. And we see that also, again, through the number of machine-to-machine connection. You can look at Gartner report, but in 2025, we are almost at 21 billion machine-to-machine connections or devices. It is projected to reach 40 billion by 2030. And what you should understand is that whenever you introduce a new electronic component, you increase your surface attack. That means that you are more, you will have more risks in the sense that you can be hacked or attacked from the cyber-physical point of view. So I think you remember what happened in Lebanon some years ago with the attack on Hezbollah through beepers. This was a cyber-physical attack. So we can control your device from very, very far away, because in every electronic device, there are what we call backdoors, simply because when you buy a computer, the mother card maybe goes through 16, 17 sites around the world, and you don't know who is putting what in this device. And this is very important because at the end of the day, Morocco does not produce any electronic device. And one of these days, we can be hacked, attacked, because we have now a very, very large attack surface. So the strategic question is, who is controlling the data, the models, but also the infrastructure? So when we talk about AI, usually we only talk about application, but I'm really focusing on the security part and the resilience part. So from the point of view of infrastructure, Today, thanks also to the AI, in fact, we can reduce the number of, let's say, attacks. I think you heard about Mythos recently, and the fact that Firefox used it to identify many holes in their security, I think up to 2071 holes that have been identified. So just to give you some numbers, there is almost 420 million attacks per day, per year. So this means 13 attacks per second. So you can do the maths just during this talk, how many attacks have been done throughout the world, and maybe some of them have been done on Morocco. So agriculture, in the agriculture market for AI is expanding as well. So in 2023, it reached $2 billion. So it's a growth of 20%. And this is, as I said before, for precision agriculture. So if I look at the defense and the drone market, a lot of people now talking about drones, and this is the trend in everything, even in agriculture. But from the defense point of view, the drone market already reached almost $40 billion, which is a growth of 14%. So why we are talking about that? We are talking about that just to motivate what we should do, but also because we have something that is very interesting to develop, which are digital twins. So up to now, thanks to AI, machine learning, data science, and so on, there were a lot of proof of concepts from R&D, different sectors, different fields, and so on. And what we are observing today is a shift from proof of concepts and R&D to core infrastructure. So in some companies like Siemens, digital twins are at the core of their business, also to simulate the entire company. So the global market for digital twins is already $25 billion, and it is projected to reach more than $150 billion by 2030. It's just huge. It's more than 30% of growth. So in terms of applications, we see them in energy, we see them in agriculture, in transport networks, in urban design, cities, territories, mines, and so on. So it is a very, very strategic sector that we should focus on. Now, when we talk about digital twins, we talk about a lot of things, because a digital twin, for those who don't know it, so is how to have a twin for something that exists. So you can think of a twin of yourself, if you want, if it is useful. But for companies, this is very important. So if we take a farm and we have a digital twin of this farm, then it means that we can prototype different, let's say, plantations before even starting doing it. And you can even compute, do a lot of simulations and decide whether or not this plantation or this plant or the other would give you the best growth, for example. So when we talk about digital twins, we talk about a lot of things, from sensing, IoT, microelectronics for sure, to data, clouds, AI analytics, simulations, and autonomous systems. So if we can control all this stack, this means that we will have a technological sovereignty. So at the core of this technology, what we see is AI machine learning, and such events that we are having today is very important for dissemination, but also to spread the field for Moroccan students and researchers, and also industry. Digital twins as well, robotics, autonomous systems, cybersecurity, cyber cryptography, advanced sensing, including quantum sensing, for example, and communication, and new materials in general, and energy systems, especially for batteries. So where can we, in fact, as Moroccan, make a strategic difference for our country? So as I said, AI, digital twins, or autonomous systems in general, they allow us to transform everything, in fact, from agriculture to defense. And for example, if we have a digital twin for a closed ecosystem, like let's take the entire planet or even just Morocco, you can really simulate everything in the field without needing to wait 10 years or even more to see what is the impact of this fertilizer or of this product on the water that you have, for example, or even for health. If we look at digital twins for companies like OCP, if we are able to link the digital twins that are produced, that are created for production, to digital twin, to organizational digital twins, then in fact we are able to completely simulate structuring of the company and see what is the effect on the market and how the feedback loop is done. So why these things matter? Because if we look at agriculture and water security, water scarcity is a real problem in Morocco. So we were very fortunate this year to have some rain, but this does not mean that it will be the case every year. Climate volatility as well, because climate is not something local. It depends on also what is happening around the world. So from AI perspective, there are many opportunities. There are yield forecasting where you can gain 25%, water optimization, as I said before, but also everything that is related to epidemiology, disease detection, soil monitoring, and so on. And now, once you link that to the drone technology, you can do really some amazing things. For energy and critical infrastructure, well, it's the same thing. Because energy is central to the Moroccan strategy to 2030. We have an increasing demand, but we also are working on renewable energy. So this means that we need to have higher grid, and it leads to higher grid complexity. So we can, for those who are living in Qanetra, for example, or near Qanetra, some of them are now facing some problems with electricity because they are building, the TGV lines. And this is something that can be avoided if we had digital twins before. So not only we can predict or forecast the demand for electricity, but you can also do predictive maintenance. We can also simulate what is the impact of hydrogen and all this new, let's say, energies that are coming up. So for industry and advanced manufacturing, we know now that Morocco has developed a strong automotive industry. The aerospace industry is also being developed very, very well. And OCP is also, everybody knows it, it's the world leader in phosphate. So having digital twins for these sectors is really very, very important. And again, we will face the predictive maintenance more and more. Now, let's go back to the subject that I like the most, which is education. So education is really a national security field or sector. It is very strategic for everybody. And as a student, you already see that most of the time, there is a delay between what you are learning at school and what is needed on the market. And today, a lot of companies they are avoiding to hire junior engineers, for example, because ChatGPT and Claude and other tools, they can do what a junior engineer does. And this is very problematic because how can you find your way in the job market if we remove the first step, which is being a junior? So any education needs to be rethink because the talent is a national power. Gen AI can be a very useful tool for that, but at the same time, if you do not control the AI systems or the LLMs, you may end up with content that you don't want to see. For example, if you ask DeepSeek and ChatGPT the same question about politics, they will give you two different answers. And this is very, very problematic. So some people think that we should have our own DeepSeek or our own ChatGPT. I'm not necessarily from this, let's say, from this family, but there are other things that we can do. What is for sure is that the trend now in education is going towards what we call personalized education. This means that within the same class, not all the students will have the same pace. And you'll have some of the students will be evolving very rapidly and others that are slower. And this does not mean that the second class are less good than the first one. But we need systems, learning systems that can adapt to the pace of learning. And also that link, in fact, the educational content to the industry skills that are needed. And this is up to now in Morocco, a real complex part. I think you are all, let's say, familiar with this problem. Don't need to go into details. So just to close this part, defense and security, they are multi-sectorial. And when we talk about defense or when we talk about national security, we are not talking only about one field. So from the point of view of defense, and we will zoom in a little bit in the next slides, we see that autonomous drones are used for a lot of things. And you don't need to be very rich to have drones. The experience of Ukraine told us that with very, very cheap drones, you can have damage that are just impressive. And also what we observed this last weeks in Emirates and Qatar, where you can see some states spending for one missile $3 million to shoot down a drone that costs $10,000. So it's really very special. We are living an era that is really, really special, and we need to adapt to it very, very quickly. So now we will be zooming on the defense side. So I know that this is not a subject that we usually treat at the university, especially in Morocco. But we should start to think about it, really. You should also follow the news, follow the geopolitical news as well, because it doesn't matter which industry you want to develop. It will always be dependent on what is happening around the world. And we are living it today. So today, from the defense point of view, AI is not just a tool. It's not a tool. AI is a domain. And in the military language, a domain means like air, like ocean, like in fact, everywhere where a war can happen. And so AI now is a domain. It has been defined as a domain, not as a tool. Its transform speed is just impressive, and it scales very well, from logistics, from everything. Also from firepower. also from how you handle information. And the real challenge today is to have, first of all, a responsible and ethical integration of AI, but you need also to be able to trust the AI tools that you are using. So now I go back to this two parallel timelines or two stories of the development of AI. So I think you are all familiar with the left one, civil AI, with the initialization, let's say, at during 56 at the Dartmouth workshop. At the same time, in fact, there was something happening at the defense side, which was the SAGE project, the first air defense C2 systems that went operational. In the 80s, from the civil side, the expert systems start to get used in industry. But before that, in 58, in the military side, ARPA and DARPA were created to avoid strategical surprises in technology in general. We waited until the beginning of 2010, 2012, where we saw the rise of AlexNet for ImageNet. And this is where really people started to think, well, we should look at this thing that is called AI. Before that, so you see that always defense is working before, in fact, civil. There was the problem of Stuxnet, which revealed, in fact, a new era of cyber-physical hacking or sabotage that can be done. 2016, AlphaGo defeated Licidal. That was a major breakthrough in AI. And at the same time, there was the project MATM that was launched at scale for ISR workflows. So ISR is intelligence, surveillance, and that are, let's say, used by the military. By the way, Maven is still used even now during what is happening in Iran. Okay, so this part is very special because this is what we teach at the bachelor level for our students. This is really a motivation before talking about AI. So everybody's talking about AI, what we can do about it, and so on. At the end of the day, they show us tables with accuracy. I am at 97%, I am at 98%, and so on. They're very happy with it. But we forget the basics. Let's forget about AI, just algorithmics, simple algorithmics. You write an algorithm that computes the trajectory of a missile. Very simple, physics and mathematics. What happened in 91 is a Patriot failure, where in fact 28 soldiers got killed because there was an error of 10 to minus 7 in the computations. Okay, very simple, nothing special. Okay, so we are not even talking about AI and machine learning algorithms that are not given 10 to minus 7 error. Okay, really keep that in mind. Sometimes you are very happy with the precision that you have, but you forget about, let's say you have a precision of 99%. And for this 1% of error that you have, you are not computing the risk. Nobody computes the risk, what you call the value at risk, that you are exposed to when your algorithms fail. And we are, in fact, in AI doing exactly what caused the crisis, the financial crisis of 2007. It's exactly the same thing. At the time, there was this tetrization and people started using it a lot. And they didn't compute the value at risk at the time. And later, there was this, there was the crisis. So the value at risk is a term for people who are doing finance, but we should also start to think about it because it's not your 99% that are important. It's what is happening for this 1% case. So another problem, algorithmic problem. So it's the Ariane 5 flight 501 in '96. And so the rocket self-destruct after 40 seconds after launch. So this was the most expensive flight in the history, because 40 seconds cost almost $400 million. And the problem was an overflow by the hardware. So now we move to the hardware. Huh? So there was also the Mars Climate Orbiter in '99, where the Mars Climate Orbiter left its trajectory again because of a bad approximation. So, here, in fact, the real problem was the units that were used were not the correct ones. So numbers, physics so the numbers were good, but the physical meaning was wrong. So these failures, what do they have in common? So from the computer side, we have finite representation of real numbers. We have also implicit numerical assumptions that we do. And we forget that error gets accumulated. And this creates really a lot of confusion. So I'll try to be very fast on what remains. So I will just briefly talk to you about what military AI is and what is not. So today, the most AI tools that are developed in the military operations are in perception systems, so image, video signals, and so on, decision support tools, and task automations. So they are changing somehow the objectives and constraints, but this puts the responsibility on humans. So we are not at little weapons that are completely autonomous. Just to give you an idea, predictive maintenance, again and again, a very important subject. So just to give you an idea, so for the Black Hawk helicopters, the US Army was able to save more than $200 million. Autonomous surveillance, now it is very, very well developed by the US. And the military drone as a market, as I said, it is really growing exponentially, as well as strategic decision supports. So I'll move to that. Okay. So let me just talk here a little bit about cybersecurity, so just to keep in mind something. Whenever you write a code, you increase the surface attack. Whenever you add a new electronic component, you increase the surface attack. So the best case, if you want to reduce your surface attack, don't use technology. But it's not the case. So I'll try to close to finish in very, very soon, because I don't have much time. But just for those who don't really know what digital twins are, so they are really a living, real-time replica of a system. So it's really like you take yourself, you have a digital twin of yourself. So it is continuously updated through sensors, models, and analytics that are implemented. It allows simulation, forecasting, optimization, decision support. So why it is important? Because it moves us from reaction to anticipation. We can have safe experiments without disrupting operations. And we can also integrate physical, cyber, and human layers into one system. So this is really foundational for autonomy and mission-critical AI. So this I already talked about. So I will just tell you now what is important for digital twins. So we have sensors that collect data. Then you put this data on the cloud or edge computing or wherever. You run your models, AI, then it feeds the digital twin. Then you go back through actuators and you close the loop like this. So digital twins are important because they will reduce the risk. They allow you to optimize even your growth, they allow you also to be resilient. And more importantly, you can be sovereign thanks to that. Okay, so there are still some slides, but I think I will just go to the end of it and talk a little bit about the opportunities for us. For us as Moroccan engineers, there are many opportunities that are there, and also many freelance, from sensors to computer vision. So people are already working on that in Morocco. Multi-agent systems, less. Human-machine teaming, less as well. Autonomous systems or navigation is still not well developed in Morocco. So autonomy is not a future concept. It is already there, already reshaping agriculture, energy, industry, civil production. And as Moroccan, we can be at the forefront of this mutation. So I'll stop here. Feel free, if you need the slides, you can ask our colleagues from Math&Maroc to share them with you. And if you have any question, I'm here, so thank you.
Thank you so much, Professor Nani, for your insightful presentation, and first for correcting and highlighting your career. You showcased through your presentation the importance of mathematics, especially contributing to the country's different sectors and helping on enforcing national security. You also presented a broader view on how AI and different emerging technologies are very important to the development of these sectors. You also gave many examples of how important they are, and they can help people survive more or prevent other incidents. You also gave us some definitions like for digital twins. I shall thank you so much for this insightful presentation again, for your presence. And now I'm giving the floor for our audience to ask their questions regarding your presentation.
Thank you.
First of all, thank you for the interesting presentation. And I have a very quick question. So you talked about the financial crisis of 2008, and there are many talks about another bubble forming, of course, the AI bubble. Do you think that there's actually a bubble, or are we, like, if there's a bubble, how do you brace for the explosion that happens after, for its popping? And if not, then how do we prepare for a world where AI will rule the technologies all around?
Well, I start by the end of the question. AI will not rule the world. AI is just amplifying what we can do. So that's already a good sign. Now, are we living a bubble? Some may say no, because they are very important actors in the bubble. Some others will say yes, because we saw that during only 1 week, the stock options got reduced by $1,000 billion during 1 week for the major technology, let's say, companies. So what we are living is so the market is. We say that it is complete. Let's say the amount of money in the market is fixed. And we have two things. We have the software and the hardware. So if you put more money in the software, this means that you are putting less money in the hardware. Okay? And it is a balance that we need to find, that they need to find. But from our point of view or our perspective, we are not even small players. We do not exist at all. You can have as many publications in the field. You does not exist. Unfortunately, this is the case. Now, what we should do, this is why let's say I do talks like this, because we need to think about this, because it is really a national security problem. AI is here. It will not leave. We should live with it. We should know how to live with it. in every sector, in education as well, in everything. So should we wait? Should we take risks? Well, we know that you have to take risks if you want to survive in the future. So you can just forget about it today and say, no, I do things as usual, nothing will happen. But in very, very few years, you'll find yourself outdated and nobody will come to you anymore. It's a risk. Really. Today, you should make bets and you should take risks and you should really think about it carefully. But talking about the bubble or not, what we see is at the end, it's only about how the money flows. And if you put more money in the hardware, this means that the software will not be developed. If you put more money in the software, this means that you think that the future will be based on the hardware of today. Well, we don't know.
To give you some context, I'm a tech professional, and I just pivoted my studies to law, private law in precision. So today, as I see the strategic imperatives and digital sovereignty and its relationship with AI and national security as focus, I see something that we can do with law, and I know that today our laws are not as going as fast as AI is, and I see that we may lack some initiatives in this sense, and I don't know if you have some idea on any initiatives in this. I think that students in law must work on this and push for Parliament to adopt more laws.
So thank you. Very important and interesting question. Who we are as Morocco, we are followers. We do not lead anything. This means that we will wait for the European Union to do their work on law, and then we will copy them. Or we wait for the US to do that job, and then we'll copy them. So we do not create, not only in law, in everything, almost everything. So we are just a copy-paster, okay? Copycat, basically. Unfortunately. Fortunately, there are already people working on that in Morocco, in different institutions, from the government to everything, really. Even the professors that I met with who are in law, for example, at Rabat, they are, let's say, open, and they want to make advancements in the field of AI for law. But the problem today, and this is why it is again linked to education, who will do the job? Engineers do not understand anything in law. And people who are studying law, they do not understand anything in AI. So the gap is so large because of the choices that we made in education. Like at high school, you have people who are following scientific field, others not. Now, is it still possible today? Today, we should have only scientific field. And then after high school, you choose whether you want to do literature or Islamic studies or whatever, because we need to have a scientific mindset. But this is really open questions. And if we lose time debating about it, we will remain only followers for the rest of our life. Unfortunately, it is like this. There is no magic in it.
We should take action.
Thank you for the insightful talk. You talked a lot about digital twins, and I wonder about how do we make sure that the digital twins that we build today, based on the data of yesterday, are able to predict, the complexities that the world has evolves into in the future.
Thank you. Very good question. And in fact, this is why we are having problems, because we think that digital twins are one-shot projects. They are not one-shot projects. They are living things. So once you start deploying your digital twin, this means that you should be working on it for the rest of your life. It's like if you build an industrial plant. You cannot just put it down and then leave the site and say, well, it will be working on its own. No, you should improve it, you should maintain it, you should revise again and again all the methods that you are using and so on. And so what is great is that the maths are evolving, the computer science is evolving as well, and many fields are evolving. And this will help us to improve these digital twins and upgrade them. But only if we think of digital twins as real ecosystems that should be shared and co-developed between academia and industry. If we put them at the industry level, they will be outdated very soon. If we put them at the academia, nothing will happen at all. They will not even be built. So we need to have something in between. So this is what we are trying to do at UM6P, in fact. So digital twins, unfortunately, they are not like the IT projects where you deploy your code and then you leave. You cannot do it like this. It is something that is co-developed. It is a living object. I don't know if I answered your question. It's fine. Thank you.
This we get 2 more questions.
Thank you for your presentation. I think that AI is very dangerous for our children. But what's the solution to protect them by AI?
To protect children with AI?
Yeah.
Well, this is also a subject that people are developing. And when we talk about AI, we should talk about data. So you need data to create something. Now, if you have data, you can build anything you want.
Especially in education.
In education, yes.
Yeah.
Education, in fact, education is, people left it for a long time since the advancement of AI. But today, education is one of the highest topics. Because in fact, the market needs change almost every 6 months because of AI and technology. So 6 months compared to the accreditation timeline, it's nothing. So how can you accredit a program if the content that is needed by the market already changed 8 times or 10 times since you started thinking about your program, education program? It's really a very complex problem. It is linked also to the administration, to the law, and so on. But today, how can we meet the expectation of a dynamical system, which is the job market, that is evolving rapidly? Something must change. And we cannot rely on ChatGPT and so on, because we do not control the content. And what we see today is that professors develop their content using ChatGPT. So you have no control on when the professor is teaching, and even the professor does not know what he will be teaching during his session, because he's discovering his content during the session. So it's weird. It's weird. But if we do not think of education as a strategic sector, as a national security sector, very soon we'll find ourselves not only using the books that were written by others, but tools that are coded by others, and we are not only people who are copying, but only consuming things. And we cannot be an emergent country and then a developed country if we keep on consuming things that are produced outside. Okay.
I think we're still going to take 1 question.
Thank you very much for your wonderful presentation. Firstly, I would like to ask you if you have something to say for the young Moroccan mathematicians who would like to choose your path and take the AI national security.
What we are trying to build at UM6P, and I really thank the Association Math&Maroc for that, because thanks to them we can spread really the vision. We are aiming to create what I call the modern Moroccan mathematical school. And if you look at, you can do a very simple exercise. Those who are, in the engineering school and they are looking for a subject to study, you can do this very nice exercise. Take all the PhDs that were defended in Morocco, okay? And try to link the PhD or the PhD students with his advisor and so on, and look at what are the subjects, though. So you create a tree, okay? And then you look at what are the subjects that are studied in Morocco. At the end of the day, you will see that all the subjects that were studied are just subjects that were exported from outside. Why? Because at a given time, there was a professor who did his PhD in Belgium, in France, in Canada, and then he came back, and then he's still continuing his work with the laboratory where he was. So we are not working on the subject that matters for us. And we saw this as well, when the NLP started before the LLM, we saw that a lot of people started working on Derija. So they thought that, no, we should have our own systems for Derija, and everybody started working on Derija. And today, nobody is using the work that they did. So we should ask ourselves the right questions. And we should work on the research subjects that are meaningful for us. So it's not that easy, like saying it today. But just do the exercise, and you will see that we are not building the skills that we need for the future. We are building the skills that other country needs. And if we keep on like this, we will never be an emergent country. We will always be in a service for a given country. And we will just change this country with another country. This is the only thing.
Thank you so much, Professor. I think we still have a long way, well, hopefully not so long way, to actually be producers of knowledge and not consumers, and maybe starting to implement our research directly to how we function and building our public policies. So I thank you again for your wonderful presentation and wonderful interactions. Now, I guess we're going to be moving from AI and national security to a bit more fundamental things about artificial intelligence with our speaker, Professor Hamza Kurti, who is an assistant professor in machine learning at UMCSP College of Computing, working in the intersection of machine learning, algebra, and cognitive science. He had focused on structured and compositional representation and learning through agent-environment interactions. He has gotten his PhD from ETH Zurich and Max Planck Institute for Intelligent Systems as a fellow of the Max Planck ETH Center for Learning Systems. He is also a Central Paris engineer graduate, holding a master's in advanced computing from Tsinghua University with prior experience in SLP. He's going to be presenting algebra at the core of artificial intelligence, from geometric deep learning to representation learning. You may come, Mr. Mustafa.
Thank you very much. Yes, so slides, and have a look at the.
Should like you to be a bit patient while we put on the show the slides of Professor Hamza.
Okay, Assalamu alaikum. So we'll have a bit of a different talk, but still related. So I want you to keep in mind this idea of digital twins. I'll tell you why in a bit. So yeah, it's great to be here. Thank you for the invitation and thank you for your efforts. I think what you're doing, like what the association is doing, is extremely important. And I encourage anyone, well, sitting here or watching us from home, to really get into such endeavors, such efforts, trying to share, right? Like trying to get out of what you're doing to trying to get benefits to more people, to a larger audience. So this is really great. And yes, I'll try to contribute as well in that regard. So my interests or biggest curiosity has been our perception system. How do we perceive? How did we learn to perceive, right? Like I want you to think about with me about this question. You have your eyes, right? And you have your brain that's sitting inside your skull, right? And your brain is completely disconnected from the outside world. And through your eyes, somehow it gets the feeling that it gets access to the information, right? It gets access to like how this scene is structured. I know the depth of this room. I know I can understand that this person is sitting in front of this person and so on. So there's a lot of inference going on, right? And it happens so seamlessly, right? It seems so easy. So this is perception, right? Like this is our perception system. And my belief is that we are in a way doing exactly what you've been describing, what you've been talking about. We have a sort of digital twin, well, not digital twin, like a neural twin, mental twin of the outside world, right? The complex system that we're modeling is the world outside, and we're maintaining this simulation of what's going on to be able to keep up, right? To be able to do so many tasks and to be able to think and plan and do. So this is what's, well, broadly, perhaps the two ideas that are interconnected here. So we have digital twin perception, well, for us, but then we want to have AI that perceives the way we do, that is as efficient, that is as intelligent, right? And so the question again is, through what principles can we have AI that perceives us as well? All right. So, okay, so it is all slides. Right, so this is what I've been talking about, right? Our perception feels effortless. It's like a background process. You don't think about it, right? And so, lots of you perhaps haven't thought about the complexity of it, right? Like how we have just access to pixels and we get concept and percepts out of it. Right, so basically we're able to do object recognition, percept extraction. You look at this room and you're able to understand it. Not only that, but you're able to track and predict in the future. If you've tried, like I did, playing table tennis, you know that you don't have to perceive now, you have to perceive the future, so that your actions are already prepared and primed for like 2 seconds ahead and so on. And the ball is so fast in table tennis, you almost cannot see it. You have to predict it. So at the core of perception, or of a lot of intelligence processes, I think we have mappings, right? So we have mappings from some domain to some other domain, right? In the case of perception, you're looking at sensory inputs, images, sounds, and signals at your cones and rods of your retina. And you're trying to map all of that, process that information, and output some sort of percepts, right? Your belief of what concepts are represented in your input. And the question is, how did we acquire that? And how can we have an AI that learns such a mapping? So we have one big problem that is called the dimensionality curves. And so when we learn mappings from data, what we're doing basically is some sort of function approximation. We have a sort of black box function and we can probe it, right? So you can see, for this input, we have this output. For this input, we have this output, and you get a sort of a data set, but you don't really know what the function is, right? So you can only have a sort of finite data set to to try to approximate your black box function. And well, it requires that you cover the input space well enough, right? So to simplify, right, if I have if I want a density of 0.1, right, for covering my input space, if my input space is just this 0,1 segment, right? If I have as an input, I don't know, like what's a one-dimensional variable? So, for example, you look at the surface of an apartment and you want to predict the price, right? So your input is one-dimensional. It's right. Here's the surface of the apartment, and for example, you can scale it down and put it into 0,1, and then you want to be able to predict accurately what will be the price. And so, if you want to have a density of 0.1 for each unit one, it means that you need 10 samples, basically, at least 10 samples to have such a coverage, equally spaced and so on. If you have two variables, suddenly you need 100 samples. And I think you're starting to see where this is going. If you look at the image space, right? The image space is how many dimensions? You have RGB, you have 256 pixels, some 256 pixels, for example. This is low resolution, and well, you need lots of samples. So basically, what I'm trying to get to is that we cannot see enough data. So this is basically impossible. We cannot cover the whole input space. So there is something else going on, right? At least for us, because we're able to perceive so well, and we haven't seen so much data. And so let's have a little exercise. This is a potassium-rich slide. So what do you see? You see it? Everyone? No issue? I drew it myself, so okay, it's good. You can see it, and so does simple AI. So, well, simple. This was quite a big model, and it's able to see that it's a banana, right? It's very confident, right? And if I show you this one, still banana, yeah? Red banana, yeah, okay. So, yeah. So something changed, but you still see the banana. Good. And if I show this to the same model, you can see that banana sits at 4th position with a confidence of 1.1%. And the first prediction is a hook. So yes, basically, it doesn't really understand the concept of a banana, or it does not understand what changes matter and what changes do not matter. So basically, the challenge is you cannot cover the whole input space to approximate your function. And it shows, right? It shows it for the AI models. For us, it does not show, right? Like our perception is quite robust. We're fine. So we must be doing something else. And we have two questions that arise from this: is what allows learning with data efficiency, which means, I mean, there's limited amount of data that I can collect from my black box function, and that I can train my model on. And then the second question, very related, which is what allows us to generalize beyond where we trained. So because I cannot cover the whole space, what allows me to, well, see some samples in some areas, some regions of the input space, and still be able to do well outside of those regions. And my answer to this, and well, some people also agree to this, is the core answer is abstraction, our ability to do abstraction. So if we have software engineers, I think abstraction for you is just something about polymorphism and the design patterns in coding, right? In object-oriented programming. But it's a lot deeper than this, and yeah, hopefully you'll walk away with a new definition that involves algebra. All right, so when we want to make a model of some reality, a digital twin, for example, so there's this quote that I like a lot. So these guys say the best material model of a cat is another, or preferably the same exact cat. So if you want a model of a cat, well, just take the same cat, or if you can, clone it, right, and work on this new cat, right? But I think you can see the joke here is that, well, you start with the initial problem, right? Like you're back to the initial problem. You have a model, but you don't have access to anything more than what you had with the initial system. So same thing, right? If you want to make a digital twin, a simulation or whatever, you could try to replicate, like some people have this ideal that if I want to make a digital twin of a very complex system, I have to like simulate every process that happens in this system, right? But then something breaks, right? Something's not right there in that it does not allow you to how to say that, like to summarize information, to get access to important information for a given task, right? If you're trying to get some decision, right? If you have the whole complexity in your model, then you're just back to the same problem. You don't have a simplification that allows you to see clear patterns and so on. So basically, this is what a good model would be. A good model would be a model that drops some of the irrelevant information and only keeps a sort of skeleton, like core skeleton of what's needed for the task. Right, and basically you need to understand how the system is composed of simpler subsystems and so on. So for example, if you have this one building, then you can have many models depending on what kind of planning you're trying to do, right? Like you have like the mechanical load diagram, you have, I don't know, electrical wiring, plumbing, right? So different systems, and you'll have different models for each of them. And each of these models are basically simplifying, like they're basically shedding away some of the complexity that you had in the initial system, right? So for example, for the mechanical load, the beam model, you're discarding everything that came with the building except for what matters for computing whether this building will collapse or not, right? You don't care about electrical wiring anymore, you don't care about anything else. So this is basically one way of seeing abstraction, right? Modeling, right? So back to the banana. So if I ask you which changes matter or which changes do not matter, which changes can I perform on this image, right? For you to still see a banana, right? You can probably think of many. I don't know if you can you think of some? What can I do to the banana without changing the percepts? Yes? You can remove the color, right? See it in black and white, still a banana, right? Yeah. Rotation, yeah. What else? Draw a line on top. Yeah. So basically, I can do a bunch of transformations, right? And I can translate it, right? I can rotate it. I can change the background, right? I can change the objects that are in the background. I can do a bunch of transformations to this image, and it's still the same percept, right? So what we've done, right, and these transformations, if you think about it, I can apply the same transformations to any input objects, right? I mean, if I had an image of an apple, if I had an image of a fish, an image of anything else, right, I can do the same thing, right? The same set of transformations, and these transformations will not impact the percepts that I should have in the output, right? Or if I'm doing AI, the label should not change, right? So these variations, they describe something called orbits, right? And I'm saying orbits because for those who are familiar, you've probably seen it's common. But anyways, so the idea is that if your function is not changed within the orbit, right? Like as you move over the orbit, your function, the outputs, the percept, the decision is not expected to change, or it changes in a very predictive way, then you have something called equivariance, right? A change in the input produces a predictable change in the output, right? And so if you have that, this is where the data economy, data efficiency comes, right? You don't have to cover the whole input space anymore, right? Because now you have multiple inputs that are associated with the same orbits, right? If they are in the same orbit, all I need to do is see one example from this orbit, right? And then generalize by predicting the way the output will change. If I know how the output changes under these variations, then I can just predict it, right? So we started with this input space, lots of data and so on. and we go to something simplified. Okay, so now we go into a deep dive to the math that allows you to do these sorts of things. So we start with groups, homomorphism. I think up to these two terms, everyone has seen, including my siblings here, right? So I think in high school, you cover groups, yeah? Yes, who remembers groups? Who is like very confident in his understanding of groups? Huh? What about homomorphisms? Homomorphisms, anyone? Yeah? High school, right? And apart from high school, nothing. I believe groups and like this group theory is extremely important for, well, so many things like abstraction, which is the core of what engineers do, right? So it's a bit of a shame that we studied group theory in high school and we stopped right where it's interesting. So we stopped at homomorphisms, right? We did not see group actions. We did not see quotient spaces and equivariance maps.
They block us and they don't give us even like where to start our research.
Okay, yeah, good. So we'll try to change that. Okay, and hopefully it matters, right? So groups is already covered, right? So you already know what a group is. I assume so, right? You are here. So you have ingredients. You have a set of abstract objects that compose in some way. You can merge two objects, compose them, multiply them, and obtain a third object within the same set, right? Internal composition. You have a unique identity element and an inverse for each element. These are just the ingredients. These are the elements, right? The object, the mathematical object that you work with. And then you have rules that relate these elements together, right? Your internal composition should be associative. Who remembers what associative means? You remember? Yeah, okay, not bad. Identity fixes all of G. This is an easy one, right? And then each element is cancelled by its inverse, right? So basically all of this. And then really what you get is a sort of abstract multiplication table, right? So this is a group. Who can tell me which group this is? This is a finite group with 6 elements. Math people? Yeah? Cyclic. Okay, this is a good attempt, but you can check that it's not cyclic. What else? I mean, I think there are only 2 groups that I can think of that have 6 elements, right? So you have the cyclic group, C6, right? And then you have 3 factorial. Anyways. Perhaps. Yeah. So this one is, I think, permutations of 3 elements. Like you have 3 elements, any 3 elements. This gives you, it has this composition structure. It's hard to see, right? If you want to see it, you have to assign to each of these elements the actual transformation, right? So this is what homomorphisms are for, right? It's transporting like the way things compose in the, like in a source group to the way they compose in a target group, right? And so it's just a map between 2 sets that happen to be groups. And the rule is that your map has to preserve the way composition happens in the input space, right? So composing then mapping is the same as mapping each and composing in the destination. Right, so we start again with this, letters that mean nothing almost. But then you can link them to other groups, right? So you can look at this set of 3 elements, any 3 dots, and you can think of the group of permutations of this sets. So each element now is how to permute, like the group G2 is how to permute these 3 elements. You have 6 permutations, right? If I take like in my hand, I take a triangle, right? And I try to tell you, like, close your eyes, and then I do a transformation of my triangle, and then you open your eyes and you see the same triangle, right? I have in my possession the ability to perform 6 operations, which are 3 rotations, right? And then reflections along the axis, right? And then again, I can also look at a 3D space, a continuous space, right? And think about what happens if I permute the 3 axes, right? what happens is a sort of, again, rotations of the 3D space and reflections of the 3D space. Again, six possible transformations. And then the homomorphism is the mapping between that assigns to each element in the G1 an element in the output group. So in total, we have here 4 groups, right? But there's a relationship between them, right? And unfortunately, this is where we stopped in terms of teaching groups and group theory. And this is, in fact, the interesting parts about groups, is you have this abstract, grid, and you try to relate it to the real world, just like I did, right? So you see groups as not just abstract elements that compose, but now you assign to each element of the group, you assign to it a transformation of some objects, whatever the object is. So yes, this is what group actions is this transition, right? Instead of just abstract objects, you go to transformations, symmetries of some other space or objects, mathematical objects. And the ingredients this time is, well, you have a group, but you do not have just a group. You also have some objects, mathematical objects, space, physical objects, whatever. And you define an external composition, which is a mapping that takes one element from your group, one element from your space, right? And you compose the two, and this gives you a new element from the space. Basically, what you're doing is you're moving your space with elements from your group, right? And the conditions are very simple. So identity has to act trivially on your space, right? Like the identity of the group, if I apply it to any space, it has to be fixed. Like the space does not change. The elements in the space do not change. And composition is respected. If I compose in the group and then move my points in the space X or the physical objects, it's the same as applying 2 successive transformations, right? I mean, under the hood, this is really just a homomorphism again, right? But it allows us to abstract, like to have one abstract idea of a group, which is defining or describing how things can be structured, right? And then say, oh, this space can be structured like that. This other space can be structured like that. This other objects can be structured like that. So just like this. So now we have one group, G, and we can define an action on the space of like these 3 dots, right? Which is a set. And then my elements here are transforming directly the elements of the space. Same thing with the triangle. Now I can define a direct action of my group on the triangle. Same thing here. So basically, in the end, I have 3 different objects, but that share the same structure, right? It's the same G that's acting on each one of them. And then I can have something called an orbit, right? So an orbit is the notion that we were looking at earlier. You take your input space, like the space that you're acting on, right? And if you keep track of this point as it transforms under the action of every element in the group, it will describe a set, right? And this set is an orbit, right? It's very simple idea, seems intuitive, but is it useful? You can see it here, okay? So, oh yeah, see, all slides. I can look at my space as the union of all orbits, right? If you think about it, if my group is acting on the space, I can think about every possible orbits that exists, right? And then any elements in my space has to sit in some orbit, right? And then I take the union of all these orbits, and it gives me back my space. But the nice thing about orbits is that they simplify the space, right? How so? This is the abstraction part. You can take your space and say, well, I don't care anymore about these transformations. I want to think about these transformations as they moving me from where I am to something completely equivalent, right? And by the way, you define an equivalence class through the orbits. So what you do is you define a new space, a simplified version of your input space. You call it the quotient space. What this is it considers each orbit as a single element, right? So if you look at this figure here, this is R2, right? And you define your orbits, right? So now you have like and the transformations is 2D rotation.
you have your orbits, which are circles, right? Can you guess what the quotient space is? Come on. If I don't care about these rotations anymore, right? Like I consider that, what is it? It's not two-dimensional, actually. The orbit is the circles, right? Are you following? The orbits are the circles, right? But if you think about like discarding this notion of rotation, you're like, I don't care anymore about this rotation. I want to see every version, every rotated version, right, of this input, right? I want to see it as a single point, right? So basically, you're collapsing the input space X, you're collapsing it into just representatives. Every circle, which is a bunch of points, you collapse them and you're like, all of you guys, I think of you as one. Do you see this? So you collapse in the orbit into 1 point, right? And what you get as a result is the quotient space. What is this quotient space? Not empty set, no. It's a line? More precisely? Real line? It's actually just half the line, right? Because you don't care about the other side anymore, right? Like this is a 180 degrees rotation, so you don't care about that. Right, so you get just R plus. And I want you to think about this. So we were talking about, I need a lot of samples, right? But now I've reduced R2, which is two-dimensional. I've reduced it to just half a line. And actually do this a lot in physics, right? So if you look for, I don't know, like, who here knows how to do like calcul de champ électrostatique? Yeah? Calcul de champ électrostatique? Yes? Electric field calculation? Okay. So if I tell you that the source, like the charge distribution, has a rotational symmetry, what do you say? The electric field has the same symmetries as the sources, right? And therefore the electric field is what? Radial, right? Right? And also it's not a function of exactly. It's not a function of the angles. It's not a function of the position on the circle, on the orbit. All the orbits share the same intensity, right? And then in terms of direction, I have something called equivariance, which is I know, like if I know the direction for this particular point in space, which is radial, right? Then I know the direction for at any point in this orbit, which is I just apply the rotation to the vector, right? So basically, the abstraction here is that you took a complex space, right? Like it was 3D space. You had to compute 3 components. Each of the components are a function of 3 parameters, right? R, theta, phi. And now you've looked at the symmetry. You've collapsed everything into studying into just one line. Now I only need to find the intensity over the line, and it's only a function of the radius. So you found invariances and you found equivariances, right? And this is the same thing that's happened. So this is science, like a scientific models. Same thing happens for mental models and AI models, right? You don't have to cover the whole input space anymore because you don't need to approximate the function everywhere. You just need to approximate it in this particular quotient space. And you can conclude what happens elsewhere. I'm not sure how I'm doing in terms of time, so stop me anytime. I think I'll manage as long as I cover this 2 slides that's come now. Okay, so basically the quotient space, now you know what it is, and you can see the economy in data. Now comes the new notion, which is equivariance. Right? We just talked about it quickly here, but who is familiar with what equivariance is? Equivariance, 1, invariance. Yeah, okay. You know invariance, but you're not familiar with equivariance. Invariance is probably more intuitive, but it's just a special case. We'll look into that. So mathematically, to talk about equivariance, now you have to think about the map itself. We talked about just the input space, right? We talked about the symmetries of the input space, that it has some transformations and so on, right? Amidst the action of a group. But now I have two spaces, the input space X, right? Which is the images and so on. And then you have an output space, which is the space of percepts, right? I mean, if I'm doing supervised learning, then I'm looking for classification. Then what I'm trying to do is take each image and put a label on it, say, well, it's an image of a banana, right? So I want to see how this mapping behaves with regard to the transformations of the input space. So now the ingredients are, I have two spaces, X and Y. Both of them admits the action of a group, the same group G. And now I ask, does my transformation F, does my mapping F, does it preserve the fact that the input space is structured by the action of G? What happens if I transform the inputs before mapping, right? And then an equivariance mapping has this formula that you see here. Basically, if I transform the inputs and then, you don't see my pointer, so I'll just do this real quick. Yeah. So if I transform the inputs, this is my inputs X, right, in the space. If I transform it and then I map it, it's the same as just transforming the mapped original inputs X, right? So this is where the, again, economy is, right? I only need to know F of X, which is the image of one input, and I can conclude what will be the output for all of these Gx, which is the orbits of X. And in terms of commutative diagrams, it looks like this. Who knows what a commutative diagram is? 1, 2, commutative diagrams? Yeah, so this is a very simple concept, and it's makes a lot of mathematical equations visual and more intuitive. So basically what I wrote here is basically the same equation that we see here. It's just saying that if I map F, like if I map X to Y through F, and then apply to it the transformation G in the output space, it's the same as first transforming the input space and then mapping the input space to the output space through the same function F. The diagram closes, right? And therefore we say the diagram commutes. And it just means that I land in the same point whether I take this path or this other path, right? Equality of the functions. Now, what is invariance? Invariance is just a special case where the action of G is trivial on the output space. It means that the G is acting on the output space. It can act on, actually, like if you wanted to, you could define the action of any group G on any space X. Do you have an idea how to do that? I mean, it sounds almost, it doesn't make sense, right? Like the symmetry groups do not need to be equal or have subgroups or so on. But what allows me to do this? What allows me to define the action of a group G on any space X? So isomorphism is the opposite of what we want. Like isomorphism would mean that this any space X can be structured by any group G. But group G, like groups, they have different structures, they have different composition laws and so on. No? You have something? So the word is here. I'm saying acts trivially on Y. When you say acts trivially, it just means that you can define a homomorphism. Any two groups, G1 and G2, you can always define a homomorphism from G1 to G2. All you need to do is the homomorphism that takes the whole group, maps it to the identity, right? And then the composition happens in the input space, in the input group, and in the output group, well, you're just composing identity with identity. So nothing, no contradiction happening there, right? It seems useless, right? But it allows us to define something extremely important, which is invariance. Now I'm going to take my group G that acts on the input space. My input space has some symmetries, translation of the image and so on. And then I'm looking at the output space, which is labels. How do we define translation on labels? Well, I'm just going to define it with a trivial action, which is translate the label means keep it the same, right? When I translate the input, the label is kept unchanged. And so this is what as an equation you see, right? It's just, if I transform the input and then I map it with F, I end up in the same place as if I did not change the inputs, right? The action G on F of X is trivial, it's just identity, right? And in terms of diagrams, it looks like this, right? Which means that wherever you are on the orbit, you land in the same destination point in the output space. Right, so I think you're starting to see basically the link perhaps between equivariance, the action of groups, orbits, quotient space, and the notion of abstraction, right? So basically you just have a rich input space, like a big input space, and you notice the symmetries and you simplify your input space through the quotient space. And then you use the fact that your function is equivariant to say that it is sufficient to look at the quotient space and not the whole input space. So this concept is widely used in deep learning. So translation is a big one, right? And it's been there for, I think now 50 years or 40 years or something like that. So here, who knows what convolutional neural networks are? CNNs? Not many. Okay. Okay, who works with AI here? Yeah, okay. But anyways, okay. But these are models, these are architectures that take into account the fact that, well, mappings from images to whatever task you want to go, or whatever output space you want to go, perhaps preserves this translation structure of images. Like an image has a translation symmetry. You can translate an image, right? So you can apply translations in the pixel space. And perhaps your mapping preserves this notion in some sense, equivariance or invariance. So this is what it looks like in terms of intermediate feature maps. So you're translating the input, and then the intermediate representations of your inputs through the processing. And this actually happens in the brain as well. Like you have different layers of your brain that preserve the topology of the 2D grid of your retina. Right? And so when you translate an image on the retina, you have a translated version of whatever processing happens in your brain as well. Right? And then you have RNNs for time shifts, right? I mean, I have time series. The dynamical laws very often are preserved whether you started at T0 or started at T0 plus T1 or something like that. And then you have spherical data, right? Not everything comes on a matrix. For example, if you're tracking, I don't know, the heat over the surface of the Earth, then you have data that is living on a sphere. And for the mathematically enabled here, you'll know that a sphere cannot be mapped in a neat way to the plane. Right, so you'll have to cut the sphere and like start to morph around, like, and destroy the metric space there, and in order to go to a plane and pass it through a CNN, right, which is what a lot of people did in the past. But you can design architectures that take into account the right symmetries of the input space. And yes, I invite you to look at, if you're interested, into the field of geometric deep learning. So back to this guy. Why did this AI fail? Right, so this model is a CNN, and as I just said, CNNs are equivalent to what kind of transformations? No, I did not say that. Exactly, I said the opposite of them. Yeah, translations, exactly. So basically, CNNs are models that are built with equivariance to translations of the image. You translate the image, you have translation of the intermediate feature maps, and you can then collapse it into something that is invariant. The last mapping is invariant, makes the whole model invariant to translations. And so it doesn't care if I translate the image, I will end up with the same prediction. But it's not equivalent to change of color, right? Because this is not a symmetry that is built in the model fails. And it doesn't fail just because it's not a symmetry that's built in. It's also failed because it's a data point that it has not explored before. So we are outside the region where the model has seen data, right? Which is also basically, I think, if I give you a blue banana, it could be the first time you see a blue banana, and you'll be able to see it as a banana. So for us, it's not a problem. But for the model, because we are outside of the domain it was trained on, its predictions are completely arbitrary. and predictable out of distribution. And so, but then again, I don't know if I'm not arguing for having this symmetry built in. Anyways, so in conclusion, you have these links between abstraction and the group theory notions that I just described. So if you want to look for transformations that don't matter, the details that don't matter, it's basically looking for the group of symmetries that you want to discard, right? And then if you want to have a model that is coherent with this abstraction that you just said, you ask whether your mappings, whether your laws are equivariant to the symmetries that you just chose, like this group that you just chose. So yeah. Right, so this is not exactly my research, what I talked about, but what I'm looking into is the fact that images and these input signals are not the first initial source of information. I don't know if you're following me on this, but you don't start, like the world does not start from the images on the retina. It starts outside of you, right? And then your eye is just measuring the state of the world. And then you're working with the images. You don't have access to the state of the world. You only have access to the measurements, right? So this is the problem that I start with. And my research is about discovering the structures instead of assuming them. So I don't know yet which group structures my input space. I'm looking for it, right? And for that, what I'm doing is I'm trying to learn the same way humans do through interaction. So basically, if you remember the digital twin cycle of life, right? So you have actuation at some point, right? So you have an action that is put into the environment to make it transform, and then you see the effect of your actions, right, materialize in in the state of the world, but you don't have access to the state of the world. You have access to measurements of the state of the world. So this is where you see the feedback of your actions. And then you're trying to use all of that. Well, that's what I'm doing, is trying to use both the observations and our ability to act, our knowledge of the actions that we perform, in order to learn equivariance and coherence mental twins of the physical world. So I'm investigating, as a structure, I'm investigating the objectiveness of the world, the fact that the world is composed, has a compositional structure made of multiple objects, right? And then, and this is with some brilliant students, Iman Rahali, and also the fact that the world is under the action of time, which makes dynamics happen, right? And so again, through interaction, trying to discover what is the structure of the state space. So yeah, that's about it. I don't know if I'm over time, perhaps. I see here 42 minutes. Okay, yeah. Sorry about that. And we're open for questions.
Thank you, Professor Hiba, for you taking us into the foundations of artificial intelligence through algebra and how understanding this parallelism between how our brain functions and how AIs are actually built. That was very interesting, giving us like a trip through group theory and how we apply it in order to do like abstraction. So I invite our audience to ask questions. Anyone?
Thank you, Hamza, for this very, very nice talk. Can we go back to the commuting diagram?
Yeah.
Nice. So normally when we talk about commuting diagrams, we talk also about the nature of the diagram, that we have complex rather than just a diagram. And sometimes you end up with elliptic complexes, like the RAM complexes and so on, that are well studied. And in fact, you can also look at the cohomological invariants of these diagrams. And if you study the cohomological invariant, you will understand what are the things that will not change by your transformation. Okay, so if we say it in just to give an idea for the audience, what are the kind of surfaces that exist? So you have like any closed surface, you take a circle. If you deform this circle by continuously, you end up with from a banana to a potato and so on. But you cannot have a donut. Okay, so now you need to add a hole, and then you can have a donut. You can have a lot of things that have only one hole, and then if you want to have other shapes, you need to have 2 holes, 3 holes, and so on. So the number of holes is what we call the Betti number, and it is in a cohomological invariance. So the reason why I'm asking this is, are we already at this level from the data point of view? And also, if we ask this question, then automatically we ask the other question: why are we only considering groups? Because we can consider any kind of transformation. If I take a banana and I continuously deform it, everyone in this room will understand that it is a banana. As long as I don't break it, and even if I break it, people will still recognize it as a banana.
Yes and no. I mean, I'm not sure I agree with that, right? I mean, if I take a banana and I transform it into a ball, because I can, right? So,
well,
topologically,
not
right?
Very far transformation.
Yeah.
Small thing.
No, but I mean, in terms of the group, right? In terms of if I go to that group, like the cohomology group, and basically describing using this invariance of Betti numbers and so on, what I'm looking at is just well, exactly that, right? Like the abstraction then is, does this object has a hole or not, right? And I mean, you can even go all the way and say that humans are basically, what are humans? Are they cylinders or? Yeah, I think basically you can go all the way and see humans as one whole object, right? Like a donut, right? But then in terms of the abstraction of perception, right, like this we use in normal life, I don't think we go into those groups, right? Like groups of deformations or of trying to, or of taking like a loop and trying to close it and see whether it collapses into a point or not, to count these numbers. But I mean, if you're interested in topological data science sort of question, right, and then asking whether my input space has holes and what's the dimension of the holes and so on, there are actually methods that's approach this question, and I think one of the most intuitive one is basically you take your like the sets of samples that you have, and you draw circles around them, and you start increasing these circles until some threshold, and if all of the circles they intersect, then basically you have this continuity, and you can draw a line that goes through all of these circles, and you have a one-dimensional hole, right? And then you can do this with like bigger and bigger circles to investigate different kinds of like higher dimensional holes.
Just to make the question more, let's say, complicated. Now,
thank you.
Now, in fact, what we describe is more like with Euclidean geometry.
Yeah, to some extent. I mean, not necessarily,
now,
but
if the image is something that we get from projective geometry, you know, you take this banana and you project it on a sphere.
Okay. Yeah, I mean, that's fine, right? I mean, I think it's a limitation that makes sense for the topic of perception, like and training AI to perceive the way humans do. Because exactly. as I said, if you go out of these groups, like SO3 and like Euclidean subgroups, reflections, color shifts, and the source. If you go to like this sort of cohomology groups and then asking whether like two surfaces are equivalent or not, I think you're going towards abstraction that we don't have and that like models should not have, right? If you take your banana, like splat it all over, I don't think you still classify it as a banana, right? If it doesn't look like a banana anymore.
Yes.
I mean, unless you have the history, right? Then it's not a method that is based on group theory. Yeah.
Thank you for your question. Well, is there anyone else?
Hello, everyone. I hope you are doing well. I shall thank our speakers for their interventions. One part that interested me in your presentation, Monsieur Hamza, c'est how the human perception work. You said that part of your research is to explore how the human perception works. So I related to the poster where I saw that I read that Monsieur Ahmed worked at INRIA laboratory, which also I related to my TPE, the project of the final project that we submit on our final year in the preparatory classes. So I did my project about cellular automata, and in order to create living like creatures inside computers, and one algorithm that they used was IMGEPs, which is intrinsically motivated goal exploration processes, which is developed at INRIA laboratory. So when during the soutenance, I was faced by the question that no matter what, we cannot develop an AI that simulates 100% the instinct or the curiosity that humans have. We cannot simulate that with our traditional ways of training AI. So I'm really curious about your response to that claim, and thank you.
Thanks for the question. I did not work in RIA. I don't know if that's what's. Oh, Ahmed, okay. Yeah. So yeah, I mean, so you're talking about goal generation. So if you want to do intrinsically motivated agents, then you need agents that are able to decide their own goals, right? And usually people just go for what did you go for? Curiosity, like surprisedness, or
like train. So cellular automata, I don't know if you want, if you know the concept. It's like a grid of cells that you decide some rules. Each cell develops its states in function of its voisinage based on the rules. So we started with the Conway game of life, and then we transitioned with the continuous cellular automata. Conway's was discrete, and then we transitioned to continuous mappings. And then, which backpropagation works only on continuous mappings. So we said why not develop an AI that automates the search of living creatures inside these systems. So, not only develop living creatures, but develop also cognitive tasks, like solve a maze. Like these creatures will be able to solve mazes and develop and solve complex tasks. So one task that was developed in a search paper was the creature is created, and then it's faced with multiple obstacles, and then it's by these process IMGEP, it would be able to solve this maze and reach the end. So each timestamp, it generates a copy of itself. If I really remember,
I don't think I'll be able to follow everything.
Yeah.
But what you're asking is basically if we'll ever be able to simulate
human instincts and curiosity to explore it. Yeah.
I mean, again, abstraction, right? What is your task? What is your goal? I mean, if your goal is really to just create another human, then you'll have to, I mean, create his whole evolution, like cultural and everything, and simulate death and hunger and everything else, and the need to procreate and everything, right? I don't know if you want to do that. I mean, and you'll have to replicate his thinking system as well, right? The machine that generates gold. I mean, people fail at just the perception part, right? I don't know if you heard about the Human Brain Project. I mean, this was a huge project in Switzerland, in I think French Switzerland, and they tried to basically have a computer that simulates like the whole brain, like the human brain. Well, we don't understand enough about the human brain to do that, and even if we did, I don't think we'll. I mean, just as Professor Ahmed talks about, like if you have just small errors in calculations, and this accumulates, and you have completely different behavior. So I don't know, like this whole fine-tuned machine that we are, I don't think you can ever simulate it as a whole. I mean, you can do abstractions for specific tasks that you have, right? Or if you have a goal in mind, you want, I don't know, to simulate the hearts and prevent disease and stuff like that, you can do that, right? But trying to replicate the whole thing, I don't see the point, right? And I don't think it's feasible, right?
I saw lately something about world models. Is it the same thing that you are working on it? And if it's not the case, what are the differences between the two fields?
It's actually a way of doing world modeling. So basically, which slides? I mean, the only difference, perhaps, or the addition that I have to world models is this desire for consistency with the geometry of the state space. So basically, a world model is just trying to replicate how your agent's actions impacts the world, right? And you do that by having a world model, you simulate it, you're having a digital twin of the outside world, right? So yeah, I mean, this is basically what you have here, which is just one special flavor of a world model. Like a normal world model, what you do is you try to replicate, to predict what will be the next state based on your current state and an action. So you have it here, but here you have it in a special formulated factorized, right? Like the action takes the form of a transformation that transforms the input space, which is not something that you normally have in world models. So this is a bit more constraining, and you don't have the guarantee that this is always true. But when it is true, you have a much better representation.
Thank you. So my question would be quite basic. We've seen that abstractions can help with economy and on the efforts put by the AI to interpret something. Here I see that your researchers are discovering the structures of the environments and by interactions. So I would like to know what is the economic viability for this, how this will help AI to improve.
Yes, so basically here it's a bit different, right? In that, in the first part of my talk I was talking about if I know the structure of the problem, if I know the structure of the problem, and I know that my mapping that I'm interested in approximating preserves that structure, then I will have economy in terms of the amount of data that I need to train. And when I say that I don't need as much data, it also means that I don't need as much compute, which if you've heard about like the amount of energy like LLM companies are consuming. I mean, now people are like, companies are investing in like nuclear reactors next to their data centers in order to power the training of the their next models. So here we're talking completely brute force, right? What I'm trying to do is, no, actually, like let's use the symmetries that we know. The problem is we don't always know the symmetries. When we don't know what the symmetries are, we're back to square one. My approaches is more about symmetry discovery, right? When you do in symmetry discovery, you're not being economical, but you will be economical once you have your model, like for the next step. Like once you have your representation and you try to do a task with that representation, then you will be economical. But before that, in building this, It is not economical, right? Because you have to explore, you have to look for what symmetries are there, what symmetries are not there, right?
I think we will take in a last question. If anyone.
I have one last question. What about category theory?
Mhm.
Can we exploit it in this sector, in AI sector?
I think you can, and there is interest in that, right? You should go and look for I think a series in YouTube called Cat for AI, which is just category theory for AI, and I think it was also an inspiration for this work, right? I mean, if you think about it, this is just a special case of a functor between two categories, right? And I mean, not in the software development, not the functional programming kind of functor, but although related. But this is a special case where the structure of the input space is a group action, but you could replace that with any other kind of structure, any kind of input category, and then a good representation would be one that defines a functor or a natural transformation from the input category to the representation category. So I think it is related. It is inspired by notions from there. Basically, I just want to enforce parallelism between the two worlds, and there is definitely efforts happening in that direction.
Any more questions? One last chance. So I should like to thank you, Professor Hinda, for your technical presentation on discovery perception from a mathematical perspective and trying to understand our own perceptions through making models that imitate how our brain works. I'm going to keep you a bit here and invite Mr. Ahmed Al-Nani to join you because Math&Maroc and also Math&Maroc has some sort of a thank you gift for you. So I should like to invite Zunub, Lieutenant Math&Maroc and Aziz Mahmoud to give you your present.